Perfect. So I'll start with the motivation. As everybody knows how IoT landscape is and how insecure it is. Then I'll a little bit talk about the motivation of the standard, which is manufacturer usage description, which is an ongoing work in IETF. Then we'll talk about our architecture, the HANZO architecture, this home area network zero operations architecture. And finally, I'll talk about the system model and the architecture itself, and then the implementation and the evaluation results as well. And finally, I'll conclude and the future work which we are doing. Just as a background, so HANZO is actually a 15th century Japanese warrior, so that's why the motivation came along with the name. Okay, so things are everywhere, right? So it's basically digitization of the physical world. And the core issue is they are insecure default configurations with them, like default passwords, default protocol configurations, be it your HTTPS, Cipher suites, or insecure TLS or Telnet protocols, right? So we have seen many attacks. The classic one is the Mirai attack, which happened 2 years back. And so on the opposite end, there's a Hajime attack, which happened sort of like, it's sort of Mirai, but it's in a good sense. So it's basically doing the same thing, wherein it's exploiting the IoT device, but it's basically breaking the device so that it cannot go into the network and create the DDoS attacks, which the Mirai bot did. Then we are seeing right now the cryptocurrency mining bots as well. And there is some crime proxies are also happening where your traffic is basically being routed by your IoT device, so that you basically it's like a Tor kind of a network. Then there is ransomware as well, and finally the classic data threat as well. So a good thing to know about is that there's a difference between the home network and an enterprise network, right? So in enterprise, you have lots of money you can spend on network administration. You can basically control your supply chain. But the issue is with home networks, wherein nobody has network administration experience. So essentially, we wanted to tackle the home network itself. So the good thing about IoT devices is they have limited functionality. So essentially, they do sense, and they basically communicate, and finally, they actuate the actual thing which really happens, right? And with this limited functionality, you have basically limited communication endpoints. So there are a limited set of communication endpoints these devices talk to. So we can exploit that particular feature of these devices, right? And on top of that, the device manufacturers essentially do two things with these devices. They basically manage the device, the software stack, the configuration, and finally the notification of what exactly when the device is seeing the network, what exactly it's doing, and it's basically sending a notification to the other services so that they can act upon the same action. So exploiting these things, So using the same logic, there's an ongoing effort at IETF called manufacturer usage description. So what exactly it's doing is essentially, it's basically a file which has a configuration which says, this particular device can do this things, and it can reach out of the network on these endpoints. And basically, it's a whitelisting of the endpoints, right? So the idea is within your local network, the IoT device, as soon as it boots up, it sends a URL, and your network basically catches the URL, and it goes to that particular URL. It downloads the file, and it installs on the local network. So okay, so this is the file format. Essentially, it has two components. So the first part is the metadata itself, what the device is, who's the manufacturer, what's the firmware version, and the second part is the actual access control list, right? So which domain the device should be allowed to access, and what is the TCP port it should be allowed to access. So that's pretty much the information it has. So using this limited information, we can basically reduce the attack surface a lot, right? So using those concepts, we started the work, and essentially the mud work requires changes in the IoT devices, right? You need to send that signal. So what we wanted essentially is to create a mud-like profile for current devices by just observing the traffic, what the device is doing. So essentially do that, and on top of that, provide a MUD manager functionality. So you should have like a unified framework wherein it supports a MUD device as well, plus the current devices as well. And and it's basically deployed on a small network as well. And the final goal was to have zero network operations. Essentially, you boot up your system, and it should just run on its own. And you should not have any administrative work at all. Okay, so moving on into the system model itself. So the approach we took is basically a network-first approach, wherein we think of network as a system itself, right? And the devices are sort of like services, which are on top of this network. And so think of this devices which are in the network, and these devices have profiles, which are essentially configurations of which device is allowed to talk to which device in the network. And once you have this communication constraint in the network, then applications basically abide by that communication constraint. Only those applications can talk to those devices wherein you have, which are there in the profile itself. So once you take this model, then you have the device state itself, right? So what exactly the life cycle of a IoT device is in the network, right? So it goes to the registration phase, then it goes to the configuration phase, and finally the operation phase. And from the operation phase, it can either go to the maintenance mode, or finally, if it's a compromised device, it can go to the quarantine state itself. So it's sort of similar to a process itself in an OS, right? So OS process has different states, and similar to that, you have device states as well in the network. So we took this concept, and this was our home testbed, essentially a classic smart home which we have. We have the electric devices which control the electric network. We have the light network, which have a couple of smart bulbs. Then we have the presence, which is smart cameras and your motion sensors. Then you have your temperature sensors, your the classic data network as well, wherein you have a mix of IoT devices and general purpose devices as well. Okay, so this is the architecture of the controller itself. So it works in 3 stages. So the first stage is the extraction state, wherein it's capturing the packets which are going to the stream. And the next stage is generation, wherein it sees the packet and it does profile generation. And finally is the delegation state, wherein it basically passes the file and delegates the enforcement control plane. So we'll talk more about the generation state. So the generation state has 3 components, essentially. So the scanner, fingerprinter, and composer. Essentially, they are self-explanatory. So what the scanner does is, as soon as the device comes into the network, it basically scans for any insecure configuration or default password in the device. So once it does that, it basically sends a signal to the device manager saying that this device has insecure password, or the protocol configuration is wrong. So you can send a signal back to the GUI, wherein you can take essentially saying that you can either do a quarantine, or you can try to basically improve the default password as well. Then the fingerprint essentially tries to create a signature of the device, whether it's an IoT device or it's a general purpose device. So you need to differentiate because you don't want your system to generate profiles for a general purpose device, which can be huge, right? So, and finally, the composer essentially creates the ACL list. So, so if a device is talking to only 4 endpoints, the composer basically monitors the network, and it creates 4 ACL entry points for that. And the system works in essentially 3 phases. First is a monitoring phase, wherein it tries to capture the device metadata, and it tries to capture the communication endpoints. Then finally, the next phase is categorization, whether it's an IoT device or a general purpose device. And the final phase is the enforcement, wherein you actually enforce the generated profile as well. So device metadata, essentially, we use a couple of methods. So no single method is actually viable here. So we use basically the link layer itself. So with the MAC address, the first 3 bytes give you the manufacturer information itself. And if you go to the DHCP option headers, you have option 55, which can give you the parameter request list, which the client is actually asking from the server. And there is an option 60, which tells the vendor class identifier. So in the figure, if you see the manufacturer, so for this particular printer, you can actually see who's the manufacturer and what kind of device it is. And it can give you the serial number as well. Then we actually tried using DNS as well, wherein you capture the set of DNS request sequences and try to see, do NS lookup and see who's the actual, where exactly the device is actually talking to, and you try to derive the manufacturer from that information. And finally, we try to do who's record as well, wherein we go to the particular domain name and we try to see, okay, who's the record for that, and where exactly the actual physical address of that particular domain is. So we try to derive it from that particular information or the manufacturer information. So these are the observations for that. So for these devices, the first one is a EasyVis. It's a camera. But if you see the link layer output, it's coming as impact pack. And if you see the whois output, it's coming as an Experian. If you see the OS, it's coming as Linux. So essentially, no single method is actually viable here. And if only for devices which have a vertical supply chain, like in this case, CP-Link or say Apple or Samsung, you will see a unified result because they control the whole the total supply chain in the system. In terms of communication endpoints, as we discussed, there are limited endpoints for IoT devices, and they actually quickly converge. So in this case, if you see the smart cameras, both of them, if the observation window is just 1 minute, you will see there are 3 endpoints, and finally after 10 minutes, it basically converges, and there is no change in the number of endpoints in the system. So this is actually a good metric. So after 10 minutes, you can actually be sure that there will be no system in the same. Okay, the signature itself. So this is the critical part wherein you have to differentiate between an IoT device and a general device. So we basically use a supervised binary classification method using support vector machines. And we basically capture the network traffic context itself, starting from the link layer, network, transport, and application. And finally, we feed this information, and the classifier gives whether it's an IoT device or a general purpose device. So once we get this information, we can go on to the profile generation for this device. Finally, the implementation part, you have the extraction stage. So we are traditionally using the TCP dump with the Python HANZO Framework. And the generation stage is actually using Python modules where there is a in-memory event bus. So as soon as everything happens, there is a publish subscribe method. And finally, the delegation stage, we are using SDN framework for that. And we use Open vSwitch. So the idea is you have all the devices in the network, and the HANZO Framework is working in parallel. And it's basically processing everything. And as soon as the device generation is done, the profile generation, it sends a signal to the ONS controller, and OS controller basically implements the flow table rules in the Open vSwitch. Finally, it creates a loop. Okay, the evaluation part. So for all the devices, the signature and the endpoints, so the framework actually does pretty well in terms of classifying the IoT device. We have pretty much 100% accuracy in that model. And in terms of endpoints, so we ran it for 20 iterations, and the endpoints basically don't change after 10 minutes. So we were pretty confident this is a good way to go ahead, especially for signatures and endpoints. But for metadata, it's tricky because Mac manufacturers are different from device manufacturers. We don't get really a good option there. And DHCP option headers are actually not implemented for IoT devices. They're implemented for general purpose devices. So that was not a good way for us. And finally, the DNS request sequence don't change, but they don't really always go to the actual manufacturer servers. Sometimes they go to the NTP servers, sometimes they go to cloud services, or sometimes to the unencrypted MQTT brokers in China. So that's not a good way for us. So in conclusion, IoT communication endpoints are actually limited, and they converge quickly. So that's a good thing. It's basically an easy way to whitelist valid network endpoints for a particular device. And in terms of metadata, there is no single method for IoT device metadata derivation. And actually, this provides a good continuous security monitoring method, wherein you basically create this device profile every 10 minutes or every 30 minutes, and you basically compare the state of the device. And if there is a change in the state, you can basically say the device is actually compromised, and you can quarantine that. So in terms of future work, actually we are porting the system to OpenWRT, and there are a couple of graduate students who are working on it. And so this is another is actually crowdsourcing the device configuration, which can be shareable in different with other gateways as well. So you don't have to go through this processing. So based on the device manufacturer and device type, you basically compare, okay, whether there's a configuration available, which is publicly available or not. And finally, questions. Right. So it's basically we're integrating Nmap framework. So it has a couple of script modules. It's like for HTTP, it basically goes out there. If there is a HTTP server, it tries to load a form as well. Then it figures out, okay, this is a form, and it tries to fuzz it saying admin. So if there is a fuzzer there, it's protocol specific essentially for HTTP, SSH, Telnet. Right. So the good thing is it's a whitelisting, right? So you're already constrained in terms of endpoints. And even if the device is compromised, it cannot go beyond those endpoints. So if it tries to go to a command and control server, which is different from those endpoints, you will already know the device is compromised.
So you mitigate it essentially by kind of forcing the device to go to a subset.
Yeah. Yeah, that's another thing. That's where the crowdsourcing comes in, wherein you have a knowledge of similar devices and how they should be configured. And if your configuration is different from them, then you already know it's already compromised.
So how do you, in that particular sense, get a list of those devices that they can find them?
In terms of?
In terms of if you want to see how much the configuration of device X differs from device Y.
Right. Right. So essentially, so the crowdsourcing it's like this is implemented on a network gateway. So the idea is there is a centralized service, maybe a cloud service, and these gateways talk to that service, saying that I have this device which is trying to basically log into my network. Do you have any configuration which is similar to this device model or something? Then if the service has seen that particular device, it will say a reply back saying that, okay, I have seen this device, and it usually talks to this endpoints.
So you have to have some trust.
Right. So there is a blockchain model that particular decentralized system has to be there. That's where we're looking at.
Any other questions?
Thank you.